Welcome softly to Dreamtime Science. Imagine you are resting in a warm room, just lit enough by a softly glowing lamp, the gentle sound of a crackling fireplace mingling with the night's hush outside. This is a sanctuary of calm stories that unfold like petals in slow motion, each word a quiet balm. If this serene space feels a little like home, a gentle tap on the like button or a subscription would help keep our lights on here, and a small note about your corner of the world would be a quiet treasure. Now, settle in, roll your shoulders loose, soften the space around your neck, and take a slow, deep breath. We will embark together on a gentle journey where knowledge dreams softly alongside you, inviting calm and curiosity to hold your mind and soothe your spirits. When you are ready, let us begin. Tonight, dear dreamers, we'll voyage on an ethereal journey into the heart of a thundercloud, where nature's spark, lightning, is born. Amidst the soft, whispering roar of the storm, we'll discover the breathtaking ballet of particles that creates this radiant electric dance. As we tread gently on the cloud's edges, let's unravel this enthralling mystery from our snug and secure stargazing spot. Now, let's illuminate our minds as gently as moonlight touching the midnight sea. Before we begin, may I ask a tiny favor? If this kind of midnight science story helps you doze, a quiet like or subscribe lets this sleepy corner of the internet keep glowing. And because I love to see how far the starlight travels, where are you listening from and what time is it there? Slip your answer into the comments below. I read them like bedtime postcards. Now take a moment, adjust your blanket, find the perfect hollow in your pillow, let your shoulders melt, breathe in and out. Ready? Then close your eyes and let's wander together. When we look up into the sky on a day that feels heavy and charged, we might catch glimpses of towering clouds silhouetted against the light, sometimes dark and heavy, other times flickering with distant flashes of lightning. These impressive formations, which we often call thunderclouds, are among nature's most powerful and fascinating phenomena. Understanding how thunderclouds form and behave during thunderstorms offers a gentle way to appreciate the intricate dance of forces and elements within our atmosphere. Thunderclouds, scientifically known as cumulonimbus clouds, are tall, dense clouds capable of producing not just rain, but thunder, lightning, hail, and extraordinary wind. Their towering shape resembles an anvil or a giant mushroom, a form that reveals much about the processes inside them. To begin with, we need to understand the basic ingredients and conditions needed for a thunderstorm to arise. The formation of a thundercloud begins with warm, moist air near the Earth's surface. This air, often heated by the sun, becomes lighter than the surrounding air and starts to rise, a process we call convection. As this air ascends, it encounters lower atmospheric pressures and cooler temperatures. Because cooler air cannot hold as much water vapor as warmer air, the moisture begins to condense into tiny water droplets, forming a cloud. At this initial stage, the cloud might still seem fluffy and white, like the common cumulus clouds we often see on pleasant days. However, When the conditions are just right, this cloud starts to grow vertically, sometimes reaching heights of 10 to 20 kilometers or more, extending through almost the entire troposphere, the lowest layer of our atmosphere. This vertical growth transforms the cloud into a cumulonimbus, signaling the potential for a full thunderstorm. Within these clouds, the dynamics are becoming more complex. The rising warm air, known as an updraft, continues to push moisture upwards, while colder, denser air sometimes begins descending in what are called downdrafts. This combination of rising and falling air currents helps to combine and separate water droplets and ice particles inside the cloud, setting the stage for the electrical activity that produces lightning and thunder. It's notable that the towering structure of a thundercloud is organized into distinctive zones, each with its own characteristics. Near the bottom, closer to the Earth's surface, the cloud is generally warm, allowing water to exist primarily as liquid droplets. As you rise through the cloud, the temperature drops below freezing, and this leads to the coexistence of supercooled water droplets, that is, water that remains liquid even below 0 degrees Celsius, and ice crystals. Within this mixed phase region, fascinating interactions occur. Small supercooled droplets tend to freeze onto larger ice particles or hailstones, a process that releases latent heat. The heat energy released when water changes phase from liquid to solid. This latent heat adds buoyancy to the updrafts, intensifying their strength and pushing the cloud even higher. This vertical development is important because the cloud grows toward the very limits of the atmosphere's stable region, the tropopause, often spreading out into the iconic anvil shape we recognize. One of the enchanting and mysterious aspects of such clouds is how they produce electrical charges that result in lightning. The mechanism behind lightning involves the separation of positive and negative charges within the cloud. As water droplets and ice particles collide within the turbulent regions of the cloud, these collisions cause electrons to be knocked off surfaces, effectively transferring charges. The upper portions of the cloud tend to accumulate positive charges, while the lower parts gather negative charges. This separation creates an enormous electrical field, a difference in charge, not unlike a giant battery inside the sky. When the electrical potential becomes strong enough to overcome the insulating properties of the air, a massive discharge occurs. Lightning, the rapid movement of the electrical charge, heats the air to temperatures hotter than the surface of the sun, causing the air to expand explosively and generate sound waves that we hear as thunder. Understanding the specific structure of the cloud helps explain where these charges accumulate and why lightning strikes tend to originate in certain zones within or around the cloud. Typically, the negative charge region near the cloud's base looks for a positive charge on the ground or in the surrounding atmosphere to complete its circuit, resulting in a spectacular and often awe-inspiring lightning strike. Another important dynamic at work in thunderclouds is precipitation formation. Within the storm, as water droplets and ice particles collide and grow, some become too heavy to remain suspended. Depending on the temperature and formation processes, these particles fall as rain, hail, or even snow. Hail forms when strong updrafts carry droplets up into very cold regions of the cloud repeatedly, allowing layers of ice to build up. The interaction of these precipitation particles and the cloud's air currents further affects the storm's intensity. The falling rain and hail drag air downward, strengthening downdrafts that often reach the ground as sudden gusts or even severe winds known as gust fronts. These outflow boundaries can influence subsequent weather patterns, sometimes triggering new storms nearby as air is lifted along their edges. It's also striking to note the timescale of a thunderstorm's life cycle. After the initial formation of the cumulonimbus cloud and development of updrafts, the storm reaches maturity, typically within 10 to 20 minutes. This mature phase is characterized by both strong updrafts feeding moisture and energy into the system, and downdrafts transporting precipitation toward the ground. Eventually, the downdrafts dominate, cutting off the supply of warm, rising air and causing the cloud to dissipate. During this life cycle, the cloud's shape often evolves. The familiar anvil-shaped top expands as the storm matures and reaches the stable stratosphere above. The spreading anvil can sometimes be bright white as sunlight reflects off ice crystals at the top, while the lower parts of the cloud appear darker and more ominous, revealing where heavy precipitation and intense electrical activity are concentrated. Beyond these physical changes, thunderclouds also influence their surroundings in atmospheric and environmental ways. They play a critical role in the Earth's water cycle by transporting moisture vertically and distributing it as rainfall. They also interact with the global electric circuit, a planetary scale system of electrical currents flowing between the Earth's surface and the upper atmosphere. Thunderstorms help maintain this balance by charging the ionosphere and affecting the electrical state of the atmosphere. The scale of thunderclouds can be impressive. Often, a single cumulonimbus can cover several kilometers horizontally while reaching tens of kilometers in altitude. Their impact is thus felt not only through the weather phenomena they generate, but also through their role in atmospheric dynamics and climate regulation. The turbulent motions inside thunderclouds can sometimes be so intense that pilots avoid flying near them, as updrafts and hail can damage aircraft. Meteorologists monitor these clouds closely using radar and satellites to track their growth and movement. The radar reflections from precipitation inside the cloud provide detailed insight into both their current state and potential dangers. In addition to monitoring, understanding thundercloud structure also guides safety advice. For instance, the dreaded flash of lightning can travel many kilometers from the cloud, making it essential for people to take shelter even when the sky overhead appears only partly cloudy. Another fascinating aspect lies in the smaller structures within the cloud called convective cells. These cells are essentially small-scale environments within the larger thundercloud, each containing its own updrafts and downdrafts. The interaction of several such cells within one storm can cause the cloud to develop complex internal patterns of precipitation and electrical activity. The concept of energy within a thundercloud also invites reflection. The cloud reflects a dynamic balance between heat, moisture, motion, and electrical charge, all components of Earth's atmospheric energy. The small water droplets and ice crystals inside the cloud store and release energy in various ways. The growth of large hailstones or raindrops converts latent heat into mechanical energy that drives the upward motion. Meanwhile, the separation of electrical charges stores potential energy, which can release violently as lightning. In quiet moments, listening to the rolling thunder after a lightning strike, one can appreciate the grand scale of processes occurring invisibly high above. The sound travels slower than the flash of light, reminding us of the enormous speeds and energy transfers happening inside the cloud. Thunderclouds are not just atmospheric curiosities, they are dynamic engines converting simple ingredients, air, water, heat, into powerful meteorological phenomena. Beyond their physical processes, thunderclouds also inspire a sense of wonder. For centuries, humans have sought to explain lightning and thunder, from myths involving gods hurling bolts to early scientific investigations by pioneers like Benjamin Franklin. Today, with advanced technology and theory, we understand the basic structure and dynamics, yet every thundercloud still holds mysteries waiting to be explored, not least because no two storms are exactly the same. One subtle but important detail in thundercloud dynamics is how geographical features influence their formation and structure. Mountains, coastlines, and even urban heat islands can provide the initial lifting mechanism that triggers warm, moist air to rise, starting the complex process. For example, mountain ranges force air upwards as it moves over them, cooling it and aiding cloud formation. This is known as orographic lifting. Coastal regions may see sea breezes push warm, moist air inland during the day, enhancing storm development. Moreover, not all thunderstorms are alike. Some are single-cell storms, relatively small and short-lived, while others form clusters or lines called squall lines, extending hundreds of kilometers with complex internal structures of multiple thunderclouds interacting. The largest and most intense are supercell thunderstorms, characterized by a rotating updraft known as a mesocyclone. These can produce severe weather, including tornadoes, and demonstrate the incredible variability within cumulonimbus clouds. When studying thunderclouds, it is also helpful to consider the role of atmospheric instability. Instability occurs when a parcel of air, if lifted, continues to rise because it is warmer and lighter than the surrounding air. This process is quantified by comparing lapse rates, the rate at which temperature decreases with height, inside the rising air versus the environment. If the environmental lapse rate is steep, meaning temperature decreases quickly with altitude, air parcels are more likely to ascend, fueling cloud growth. This brings us back to convection, the fundamental engine of thundercloud development. It is fascinating to see how simple physical principles, warm air rising because it's less dense, water vapor condensing into droplets releasing heat, droplets colliding to generate electrical charges, and gravity pulling precipitation downward, all interlock to produce such a complex and awe-inspiring cloud. From a chemical and microscopic perspective, the cloud's makeup includes countless tiny droplets and ice crystals, each no bigger than a fraction of a millimeter. These act as the fundamental building blocks. They interact not only with each other, but with aerosols, small particles suspended in the air such as dust or pollution, which can influence cloud microphysics and storm behavior. In modern meteorology, studying thunderclouds also involves remote sensing techniques. Weather satellites equipped with infrared sensors measure the temperature of cloud tops and their vertical extent, while Doppler radar reveals interior motions by detecting the velocity of precipitation particles. These tools help forecasters understand storm intensity and evolution, ultimately improving warning systems to protect lives. One more aspect worthy of gentle thought is how these atmospheric giants connect with larger climate systems and phenomena. Thunderstorms are integral to the Hadley cell circulation that governs tropical climates. Their towering clouds release vast amounts of heat and moisture into the upper atmosphere, influencing jet streams and the distribution of energy around the planet. In this sense, thunderclouds are both the creators of local weather and contributors to global atmospheric patterns. As we meditate on the humble beginnings of a thundercloud, invisible water vapor rising to become towering ice and water droplets charged with electricity and energized by heat, it becomes clear that these clouds represent a crossroads of physical forces. The next time you see a thundercloud rolling across the horizon, you'll know it is far more than a simple puff of vapor. It is a living laboratory where physics, chemistry, and Earth's energy flows come alive, orchestrating the magnificent storm that is thunder and lightning. In closing this reflection on the structure and dynamics of thunderclouds, it's comforting to recall that these clouds, while powerful and sometimes dangerous, are also transient visitors in our sky. Each storm has a life, a cycle of growth, maturity, and dissipation, after which the atmosphere resumes its quiet state until conditions arise anew. Our understanding of these storms deepens with every question we ask and every observation we make, reminding us that nature's mysteries are best approached with both curiosity and reverence. So, as your mind drifts with the fading rumble of thunder, carry with you the knowledge that above, in the quiet heights of the atmosphere, tumultuous grandeur unfolds within the soaring cumulonimbus, shaping the weather we experience and linking us all to the breath and pulse of our planet. The lightning flashes are not just moments of fleeting light, but rather the visible highlights of an ongoing and intricate atmospheric ballet, a performance of physics and energy that invites us gently to look up and wonder. Thunderstorms hold a kind of quiet magic. Their towering clouds, lattice-like with ice crystals and water droplets, seem to brew something extraordinary within their depths. What most of us see is the dazzling flash of lightning, a brilliant spectacle of nature's power, but beneath it lies a subtle and intricate dance of microscopic particles and invisible forces quietly crafting the electrical storm. Today, let's take a slow and gentle journey through the heart of a thundercloud to understand how these clouds create electrical imbalances, the very seeds of lightning, through a process known as charge separation. To grasp what happens inside a thunderstorm, we first need to appreciate that air, water, and ice are more than just the elements we breathe and see. They also carry electric charges. In fact, every atom and molecule can hold a tiny electric charge, either positive or negative. The key to thunderstorms is how these charges become separated, much like when you rub a balloon on your hair and it sticks to a wall. The rubbing causes electrons, which are negatively charged particles, to move from one object to another, leaving one positively charged and the other negatively charged. This simple transfer of charges is mirrored on a massively larger scale inside a thundercloud. High above the ground, towering clouds climb as tall as mountains. These are cumulonimbus clouds, sometimes stretching up to 10 kilometers or more into the sky. Within these clouds, temperatures vary dramatically, from above freezing near the top down to warm and moist near the bottom. This vertical temperature gradient creates an environment where various forms of water coexist, from tiny supercooled water droplets to larger ice crystals, hailstones, and graupel, soft hail or snow pellets. This mixture is crucial for the charging process. At first, it might be puzzling to understand why particles inside these clouds, all floating freely in air, choose to separate into positively and negatively charged zones. The answer lies in collisions and the physics of particles. Water droplets and ice particles are constantly moving, carried by strong updrafts and downdrafts, colliding and bouncing off each other. But when certain types of particles collide under specific temperature conditions, electrical charges transfer between them. One classic model to explain this is the non-inductive charging mechanism. It involves interactions between tiny ice crystals and larger graupel particles. When these collide, electrons move from one particle to another. Usually the smaller, lighter ice crystals become positively charged, while the heavier graupel gains a negative charge. The exact physics is still an active area of research, but temperature plays a role. These charge transfers tend to happen most efficiently at temperatures between about 10 degrees and 20 degrees. Because ice crystals are buoyant, they are carried upwards by updraft winds, rising gently higher into colder regions of the cloud. The heavier Graupel particles, now negatively charged, begin to fall or hover lower down. This vertical sorting process leads to a spatial separation of charges. Over time, the cloud organizes itself into layers of positive charge near the top and negative charge near the middle to lower regions. Interestingly, a smaller positive charge region often forms near the cloud base or even just beneath the thundercloud. This results in a tripolar charge structure, a large positive charge at the top, a significant negative charge in the middle, and a smaller positive charge near the bottom. This pattern is not universal, but it's common enough to be central in lightning formation. To put the scale of these charges into perspective, consider that the electrical potential difference, or voltage, within a thundercloud can reach hundreds of millions of volts. This immense voltage is generated by the separation of charges over distances of several kilometers inside the cloud. But even more remarkable is the fact that the atmosphere around us is typically an excellent insulator. The air resists the flow of electric current, preventing charges from moving freely through it. So the question arises, how can this static separation lead to the sudden discharge we know as lightning? To answer this, it helps to recall the principle that opposite charges attract. With large charges of opposite sign separated in space inside and under the cloud, strong electric fields develop. An electric field describes the force per unit charge that a charge would experience in the space surrounding the charged bodies, somewhat like the invisible lines of force you might have seen illustrated in physics textbooks. When these electric fields become sufficiently strong, they can overcome the insulating properties of air. The air molecules begin to ionize, that is, their atoms lose electrons, becoming charged ions. This ionization starts a cascade effect where free electrons accelerate and hit other molecules, freeing more electrons and creating a conductive path. This path is the beginning of the lightning channel. But before the lightning flash itself, the cloud must have developed this electrical imbalance. The processes of charge separation take place over minutes or even tens of minutes in a growing thunderstorm. This patient build-up contrasts sharply with the rapid discharge of electricity, which unfolds in mere fractions of a second. Let's take a closer look at the conditions inside the cloud that create these environments conducive to charge separation. The tempestuous atmosphere inside a thunderstorm is fueled by convective currents. Warm, moist air rises rapidly and cools as it reaches higher altitudes. Cooling causes water vapor to condense into droplets, releasing latent heat, which in turn keeps the air buoyant and the updrafts strong. These updrafts carry droplets and ice high into the colder regions of the cloud. There, supercooled water droplets, liquid water existing at temperatures below freezing, coexist with ice crystals. This unusual coexistence is critical for charge transfer. Supercooled droplets can freeze onto ice particles, making them grow rapidly and creating Graupel pellets. When these heavier particles fall and collide with smaller ice crystals in the temperature range mentioned earlier, charge transfer occurs. Experiments have determined that the sign and magnitude of charge transferred depend not only on temperature, but also on the liquid water content, the size of the particles, and their relative velocities during collisions. The resulting microphysics set the stage for charge distribution. Positive charges tend to collect on the smaller ice crystals which updrafts carry upwards. The graupel, bearing negative charge, accumulates lower down. Collisions and rebounds continue throughout the cloud, reinforcing the charge segregation. This leads us to the idea that a thundercloud is essentially a giant capacitor, a device designed to store electrical energy by separating opposite charges. Capacitors have two conductive plates separated by an insulator. In clouds, the plates are replaced by charged regions separated by air, which acts as the insulating medium. Capacitors store energy in the electric field between their plates. Similarly, the thundercloud stores immense electrical energy in the strong fields created by charge separation. When these fields cross a critical threshold, the air breaks down and lightning acts like the capacitor suddenly discharging. Another factor aiding the buildup of electrical imbalance is the movement of the cloud as a whole. Wind shear, variations in wind speed and direction with altitude, can tilt or stretch parts of the storm, maintaining distinct zones where charges segregate, preventing charges from simply mixing and neutralizing. This dynamic nature helps maintain the electrical imbalance over time. But the story does not end just with the ice particles and updrafts. The strong electrical fields inside the storm can also influence the movement of charged aerosols and ions around and below the cloud. The positive charge near the cloud base often induces a mirror negative charge on the Earth's surface, setting up a powerful potential difference that ultimately guides where lightning will strike. This attraction between the cloud charges and the ground charges is another key part of the system. It means that electrical imbalances are not confined to the sky, but extend to the Earth's surface at the foot of the storm. As the electric field grows stronger, it starts influencing the paths of electrons in the intervening air. Long before the main lightning leader channels begin, tiny steps of ionized air, called stepped leaders, start propagating downward in zigzag paths, searching for a connection with a positively charged surge from the ground. These explorations, invisible and almost imperceptible, are the physical manifestation of the electrical imbalances reaching a critical point. Each separate leader is a faint cold plasma channel carved by the electric field across the air. Eventually, when a leader from the cloud and an opposite polarity leader from the ground meet, a complete channel forms. The lightning bolt races along this channel, neutralizing the charge separation in an explosive exchange of energy. It's worth noticing how remarkable this whole process is, that countless tiny, chaotic collisions between ice particles, driven by nothing more than the natural thermodynamics of the atmosphere, can lead to such an ordered and magnificent electrical phenomenon. This charge separation process in thunderstorms is not only fascinating physics, but also vital for life on Earth. Lightning discharges help maintain the global electric circuit and even fertilize soils by converting atmospheric nitrogen into biologically useful compounds through the high temperatures and energies in the lightning channel. In a sense, the thunderstorms provide a natural mechanism linking the sky, the earth, and the chemistry of life. Returning gently to the cloud itself, let's consider how nature regulates this charge separation. Thunderstorms only last so long, they dissipate, losing energy and structure. When the efficient transport of ice crystals and graupel particles ceases, collisions become less frequent, and the charge separation fades. The electrical imbalances then diminish, the cloud's potentials reduce, and lightning activity slows down. Sometimes strong updrafts move through the same region repeatedly, allowing sustained charging and multiple lightning strokes. In other cases, the storm weakens, the charges recombine, and calm returns. The balancing act inside thunderstorms is delicate and powerful. Tiny particles, driven by enormous currents of air, collide in sub-freezing temperatures, exchanging electrons and sorting themselves by weight and charge. This dance creates vast, invisible structures of electrical potential, setting the stage for some of nature's most spectacular shows. The light and sound of lightning are just the climax of a slow, unseen symphony played by physics, chemistry, and meteorology inside a cloud. As we reflect on the mysteries of these glistening giants of the sky, we realize that thunderstorms are not mere weather events, but complex natural laboratories, showcasing fundamental principles like charge separation. They remind us that the smallest interactions can lead to immense forces, and that the mixed phases of water, liquid, and solid are critical players in the sky's electrical drama. So next time a storm gathers and the first distant rumbles echo faintly, allow yourself to sense the slow, patient build-up inside those clouds. Know that unseen forces are at work, microscopic ice particles hitching rides on gusty currents, trading charges in a silent exchange, while the atmosphere holds its breath until the moment it lets go in a brilliant, electrifying flash. In these processes, science reveals not only the mechanisms behind lightning, but also hints at the interconnectedness of nature's systems, how gentle collisions of specks of ice contribute to the powerful currents lighting up the night sky, stitching together the earth, sky, and living world in an unseen web of energy and charge. It is a testament to the elegance of the natural world that such tremendous electrical storms arise from such subtle origins. As you settle more deeply into rest, let these quiet, wondrous mechanisms of the storm lull your mind. From the microphysics of ice crystal collisions to the dance of charged particles overhead, the story of charge separation within thunderstorms is a story of balance, energy transfer, and the deep, patient forces shaping our planet's weather and life itself. May these reflections bring you a sense of calm curiosity and awe as the thunderclouds drift across the sky and the world turns, charged and alive with unseen electric artistry. Sleep well, knowing that science continues to unravel these mysteries, just as the storm patiently gathers its power moment by moment in the slow, steady rhythm of the atmosphere's great symphony. In the vast expanse of the atmosphere, where invisible forces play with water droplets and ice crystals, a remarkable process unfolds, one that culminates in the sudden, dazzling spectacle of lightning. To understand how electrical charges accumulate inside clouds and ultimately unleash those brilliant lightning discharges, we need to gently explore the delicate interplay of physics, chemistry, and meteorology. Clouds, by their nature, are collections of countless tiny water droplets or ice particles suspended in the air. Within certain types of clouds, particularly the towering cumulonimbus clouds, often called thunderclouds, a complex dance of particles constantly occurs. This dance is more than mere drifting and collision. It is the stage where electrical charges are stirred and separated, setting the stage for lightning. Let's begin by considering what happens inside a cumulonimbus cloud. These clouds are formed from rising warm air laden with moisture. As the moist air ascends, it cools, and the water vapor condenses into minute droplets. As the upward motion continues, some droplets freeze, forming small ice particles. Meanwhile, at various heights in the cloud, conditions vary. Up high, temperatures dip well below freezing, conjuring ice crystals. Lower down, droplets might remain liquid, or begin to become supercooled, meaning they stay liquid even below 0 degrees Celsius. Here lies the foundation for electrical charge separation. For an electric charge to build up, particles within the cloud must somehow gain or lose electrons, those tiny particles orbiting atoms that carry a negative charge. The story of lightning starts with the collisions among these cloud particles. Ice crystals, gropal, soft hailstones, and supercooled droplets. When these particles collide, a process called charge transfer or triboelectric charging can happen. This is akin to rubbing a balloon on your hair and watching static cling, but on a vast, invisible scale. Scientists have carefully studied laboratory experiments that simulate these collisions and have observed a consistent pattern. When small ice crystals collide with larger, softer hail particles called gropal, the hail tends to gain negative charge, while the smaller ice crystals gain positive charge. Why does this happen? The answer lies partly in temperature, partly in how the particles are composed and their physical states. When a gropal particle is slightly warmer and coated with a thin layer of liquid water due to freezing on its surface, and it collides with a colder ice crystal, electrons tend to transfer from the warmer gropal to the colder ice crystal. This leaves the gropal negatively charged and the smaller ice crystal positively charged. Air currents inside the cloud are essential actors here. Updrafts, strong vertical winds rushing upward, can carry small, positively charged ice crystals high into the upper parts of the cloud, where temperatures are extremely low and the air is thin. Meanwhile, the negatively charged grapple particles, being heavier and larger, tend to fall or hover lower in the cloud. This separation, stacking positive charges near the cloud top and negative charges lower down, effectively creates an enormous electric field inside the cloud. A field like this is a region where electric forces exert pressure and influence over charged particles in the surrounding air. To put it simply, the cloud becomes polarized, almost like a giant natural battery or capacitor with separated charges waiting for a pathway to equalize. The ground beneath the cloud often plays a role too. The negative charge at the cloud base can induce a positive charge on the Earth's surface beneath it, setting up an even stronger electric tug-of-war across the distance between cloud and ground. But the cloud's potential electric energy is held back by the insulating power of the air itself. Air is normally an excellent insulator, which means it does not allow electric charges to flow freely. For the charges inside the cloud to suddenly discharge as lightning, the electric field must become so strong that it overwhelms the insulating properties of air. As electrical charges accumulate and the electric field strengthens, tiny sparks called streamers begin to form within the cloud or between cloud and ground, typically invisible or faint at first. These streamers are channels of ionized air, a state of air with free electrons and positively charged ions, which can conduct electricity. Once a streamer connects a charged region to another area of opposite charge, whether deeper in the cloud, another cloud, or the Earth's surface, it forms a conductive path along which a massive electrical current can flow. This initial step leads to the lightning stroke we can see, a sudden, intense flow of electric current traveling through the ionized channel formed by the streamer and further strengthened by the heating and expansion of the air, creating the brilliant flash and thunderous shock wave. Digging deeper into the cloud microphysics, the process of charge separation depends not only on collisions, but also on the vertical structure of the cloud. Studies using radar and aircraft have shown that frequently the cloud's upper regions carry a strong positive charge, while the lower regions hold a dominant negative charge. Sometimes a smaller layer of positive charge exists near the cloud base, leading to complex layered charge structures. This layered structure explains not only the typical cloud-to-ground lightning, but also phenomena like intra-cloud lightning, the branching, flickering discharges that often happen within the cloud itself, never striking the ground. One subtlety worth noting is the role of temperature regions within the cloud. The charge separation process is most efficient where temperatures lie between about 10 and 20 degrees Celsius. This is because, in this range, supercooled water droplets, ice crystals, and grapple coexist, allowing frequent collisions and charge exchanges to occur. In warmer parts of the cloud, where water remains liquid and no ice forms, charge separation is minimal, and in the colder extremes, collisions are less frequent. The interplay of temperature, particle size, and phase of water creates an environment optimized for building up strong electric fields. Another fascinating aspect is how tiny differences in initial charges and droplet or particle sizes can vastly influence the electric field's development, leading to differences in lightning frequency and intensity in storms. One might also ask, what limits the buildup of charges inside the cloud? Clouds cannot accumulate infinite charge because as the electric field grows stronger, it begins to drive unwanted electrical discharges, leakage currents, or smaller sparks that partially neutralize the accumulated charge. Additionally, environmental conditions such as humidity, wind shear, and aerosols, tiny particles in the air, can influence how charges are generated and separated. Some scientists also explore the role of cosmic rays, high-energy particles from outer space, in initiating air ionization that may lead to the first charged bridges triggering lightning. Though this remains an active area of research, the cosmic rays can produce ions in the atmosphere, potentially affecting the conductivity and helping or hindering lightning initiation. Putting these pieces together offers a compelling picture of lightning's genesis as both a microscopic and macroscopic phenomenon. Each tiny collision among ice particles is a minuscule electrical encounter, yet millions upon millions of these collisions, orchestrated by the cloud's turbulent motions, produce enough charge to energize an immense flash of lightning visible across miles. The time scale involved in this charge buildup is also intriguing. The electrification process can take minutes to tens of minutes, during which updrafts and particle collisions accumulate charges. When the built-up charge reaches a critical threshold, the discharge, lightning, happens in a fraction of a second. As the lightning stroke passes, it momentarily neutralizes or redistributes charges inside the cloud and between the cloud and ground. Following it, the electrification process resumes, rebuilding towards another potential discharge. Moving back to the cloud's physical structure, the role of turbulence deserves deeper mention. Turbulence within the cloud causes the particles to collide more frequently and randomly, increasing charge separation efficiency. The chaotic swirling air currents also weave the charged particles into complex spatial distributions, generating regions of varying electric potential that favor the initiation of electrical discharges. Even cloud size impacts the abilities to generate lightning. Larger and taller cumulonimbus clouds, sometimes exceeding heights of 12,000 meters, nearly 40,000 feet, with robust updrafts, tend to produce more intense electrical separations and frequent lightning. Smaller clouds with weaker vertical motions often lack the conditions needed for the strong charge separation necessary for lightning. Over many decades, scientists have developed tools to study these processes. Aircraft instrumented with probes fly into thunderclouds, measuring electric fields and particle types. Ground-based lightning detection networks pin down the timing and location of strikes. satellites observe lightning flashes from space, and high-speed cameras reveal the fine branching structures of lightning strokes. Together, these measurements feed into numerical models that attempt to simulate how charges grow and discharge inside clouds. These models incorporate the physics of microphysical particles, electrical forces, and atmospheric dynamics to predict lightning activity and intensity, helping to understand not only thunderstorm behavior, but also broader climate and atmospheric chemistry impacts. Understanding charge accumulation and lightning also has profound practical importance. Lightning remains one of nature's most powerful electrical hazards, posing risks to life, infrastructure, and aviation. Knowledge about lightning generation helps develop better prediction systems, safety protocols, and lightning protection technologies like lightning rods and grounding systems. Moreover, lightning plays a significant role in the nitrogen cycle, because the extreme temperatures of lightning flashes cause nitrogen and oxygen in the atmosphere to react and produce nitrogen oxides, vital nutrients for soil fertility. When the cloud's internal electric field becomes sufficiently strong, often on the order of hundreds of thousands of volts per meter within the relatively thin air gaps between particles, the breakdown of air molecules creates a cascade of ionization leading to the spectacular lightning stroke. In summary, the accumulation of electrical charges inside clouds is a result of numerous small processes, the collisions among differently sized ice and water particles, the transfer of electrons influenced by temperature and phase changes, the vertical sorting of charged particles by turbulent winds, and the strong but temporary imbalance of charges that builds over time. Once a critical point is reached, the stored electrical energy is discharged via lightning, a sudden neutralization that lights up the sky. The mystery of lightning is, therefore, an elegant story of natural physics woven into the fabric of weather phenomena. It demonstrates how subtle physical interactions at microscopic scales lead to breathtaking and powerful events at macroscopic scales. Lightning is not simply a bolt of electricity, but the visible result of countless tiny encounters where nature's particles trade electrons, dance in turbulent air, and through a gradual accumulation of charge transform into one of the most awe-inspiring natural displays. So, the next time you witness a storm gathering on the horizon, or marvel at a flash of lightning arcing over the landscape, you can appreciate the intricate and gently building electric drama playing out invisibly within the clouds. The atmosphere becomes a grand theatre of particles and forces where electrical charges gather patiently, separated by invisible currents, until the luminous strike of lightning finally lets the spark of understanding and light travel across the sky. Lightning is one of nature's most electrifying phenomena, quite literally, and its formation is not just a spectacular flash that lights the sky during a storm. When we examine lightning closely, we find it sits at the intersection of weather systems and atmospheric chemistry, influencing both in profound ways. Understanding lightning's broader implications helps us unravel complex processes that govern our atmosphere and even affect the environment at large. So let's gently explore what causes lightning and, stepping further, how it shapes weather patterns and atmospheric chemistry. To start, lightning begins inside towering storm clouds, known scientifically as cumulonimbus clouds. Within these clouds, rising warm air and descending cooler air create turbulent motions called updrafts and downdrafts. As water particles in different forms, liquid droplets, ice crystals, and hailstones, which are frozen raindrops, move around this turbulent environment, they collide with one another. These collisions cause tiny electric charges to separate, a process termed charge separation. The key detail here is that different types of particles acquire different electrical charges. Lighter ice crystals often gain positive charges and are carried upwards by the updrafts, while heavier hailstones and water droplets assume negative charges and tend to settle lower in the cloud. This movement sets up a large-scale electric field with a build-up of negative charge, typically near the cloud's base, and positive charge near the top. When the electric field becomes intense enough, it overcomes the insulating ability of the surrounding air, causing a sudden discharge of electricity we see as lightning. But we don't just stop at the cloud itself. Sometimes lightning can extend from the cloud to the ground, or between clouds, making it an important player across large areas of the sky. Its formation, in essence, is both a symptom of the weather conditions inside the storm and a catalyst that subtly influences other atmospheric processes. One of the most interesting broad implications of lightning formation is its role in the dynamics of weather systems. Lightning is not just a consequence of storms, it serves as a marker of storm intensity and development. For meteorologists, the frequency and distribution of lightning within a storm hint at the storm's vigor and potential severity. When a thunderstorm exhibits frequent lightning strikes, it often indicates a strong convective process, vigorous rising of warm, moist air, fueling the cloud's growth. This, in turn, points to robust rain production, possible hail formation, and even the likelihood of tornadoes in extreme cases. Moreover, the electrical activity in thunderstorms indicated by lightning is intertwined with processes that influence precipitation. The presence of large ice particles and liquid water droplets together promotes collision and freezing processes that encourage rain formation. These collisions within the storm are responsible for the charge separation that generates lightning. Therefore, the same mechanisms that create lightning also help drive the precipitation cycle, linking lightning directly to the weather's hydrological aspects. Lightning also affects the atmospheric layers vertically. The electric discharges release enormous amounts of energy, heating the surrounding air instantaneously to temperatures near 30,000 Kelvin, much hotter than the surface of the sun. This sudden, intense heating causes the air to expand explosively, producing thunder. But the heating also has chemical consequences. The energy breaks molecular nitrogen, N2, and oxygen, O2, apart, allowing atoms to recombine into new molecules such as nitrogen oxides or NOx, NO and NO2. This process introduces reactive nitrogen species into the atmosphere, which have further implications. These nitrogen oxides produced by lightning are important for atmospheric chemistry, acting as catalysts in reactions that form ozone, O3, in the troposphere, the lower part of the atmosphere where weather happens. Unlike the protective ozone layer high up in the stratosphere, which shields us from harmful ultraviolet rays, tropospheric ozone is a reactive greenhouse gas and a component of smog. Lightning-induced nitrogen oxides contribute to this ozone formation, influencing air quality and climate. In effect, lightning doesn't just redecorate the sky with brilliant flashes, it physically changes the chemical composition of the air around us. By introducing nitrogen oxides into the atmosphere, it participates in a natural but delicate balance involving pollutant levels, greenhouse gases, and the oxidative capacity of the atmosphere. The atmosphere's ability to self-clean by breaking down pollutants. Considering this, it becomes clear that lightning plays a unique and often underappreciated role in linking weather phenomena and air chemistry. It acts as a natural engine of chemical change, altering the atmosphere in ways that ripple through both local environments and global systems. Another compelling implication concerns the Earth's global nitrogen cycle, which is critical to life itself. Nitrogen gas makes up nearly 78% of our atmosphere, yet it is largely inert and unusable by most living organisms in that form. Nitrogen must be fixed, which means converted into compounds like nitrates and ammonium that plants and microbes can absorb and use to grow. Commonly, nitrogen fixation occurs biologically in soil bacteria or through industrial processes, but lightning is also a natural nitrogen fixer. When lightning breaks nitrogen molecules and oxygen apart, recombining them to nitrogen oxides, these oxides dissolve in rainwater, creating nitrates that fall to the ground with precipitation. This rain delivers bioavailable nitrogen to ecosystems, fertilizing plants and supporting the food chain. So lightning is an important, though less obvious, contributor to maintaining soil fertility, especially in regions where biological nitrogen fixation is limited. This relationship highlights the intricate and interconnected nature of atmospheric electricity, chemistry, and life. On the scale of entire weather systems, lightning activity correlates with the development of significant phenomena such as tropical storms and hurricanes. While these large systems are powered mainly by warm ocean waters fueling atmospheric instability, lightning provides clues about their inner dynamics. Researchers observe that an increase in lightning frequency often precedes intensification phases in tropical cyclones. This suggests that lightning is a useful indicator for the internal mixing and convection strength inside these powerful storms. Here again, lightning acts as a messenger, carrying information about the state and evolution of complex weather systems. Moving from the chemical and meteorological perspectives to a more global view, it is important to recognize lightning's role in atmospheric electricity. Our planet is constantly surrounded by an electric field maintained by the continuous exchange of charges between the Earth's surface and the ionosphere far above. Thunderstorms, with their electric currents and lightning discharges, help maintain this atmospheric electric circuit called the global electric circuit. Every lightning strike moves charge and energy between the cloud and ground, contributing to this global circuit. Electron flows and ions generated by lightning discharges influence the electrical properties of the atmosphere and even impact phenomena such as the auroras near the poles or the behavior of cosmic rays entering Earth's atmosphere. Thus, lightning is part of a grand electrical system that governs many atmospheric processes beyond any single storm or weather event. Furthermore, lightning's effects on the atmosphere go beyond chemistry and electricity. They have climatic implications. The nitrogen oxides produced through lightning-triggered fixation can influence the greenhouse gas balance in the atmosphere. For instance, nitrogen oxides are involved in the formation and destruction of ozone, which, as I mentioned, acts as a greenhouse gas. Ozone near the Earth's surface traps heat, affecting regional temperatures and contributing to climate feedback loops. Scientists study how changes in global lightning frequency may respond to warming climates because rising temperatures increase the energy and moisture available to storms, potentially enhancing convection and lightning activity. This could form a feedback mechanism where more lightning results in more nitrogen oxides, more ozone, and additional warming, a subtle but noteworthy interaction in the intricate climate web. Not forgetting the human dimension, lightning's relationship with weather systems and atmospheric chemistry influences us in various ways. Lightning ignites wildfires, particularly in dry regions, which alters ecosystems, releases stored carbon dioxide into the atmosphere, and affects air quality for humans and animals alike. These fires can drastically reshape landscapes, and their frequency and intensity are connected indirectly to lightning patterns dictated by weather. Additionally, the nitrogen oxides from lightning form part of the air pollution balance. Although lightning's contribution to nitrogen oxides is dwarfed by human-made sources such as vehicle exhaust and industrial emissions, it provides a natural baseline that influences how these pollutants behave chemically in the atmosphere. This understanding helps scientists model air quality and develop strategies to manage human impacts on the environment responsibly. Interestingly, studying lightning also holds practical benefits for weather prediction. Lightning detection networks provide continuous real-time data about storm activity worldwide, improving forecasting accuracy. Lightning frequency, distribution, and intensity serve as proxies for storm strength, helping predict severe weather phenomena like flash floods, hailstorms, and tornadoes. This ability to read lightning patterns enhances early warning systems, improving public safety and preparedness. In a broader scientific context, lightning offers a fascinating laboratory for studying plasma physics and energetic chemical reactions. The conditions inside a lightning channel, extreme temperatures and pressures, mimic, on a small scale, processes that occur in plasma devices and astrophysical environments. By carefully examining lightning, scientists learn about electric discharges, ionization processes, and energy transfer that have applications in technology and fundamental science. To sum up, lightning formation is not an isolated curiosity limited to dramatic visual displays in the sky. Its implications reach deeply into the workings of weather systems, influencing storm strength, precipitation processes, and atmospheric convection. Its chemical products, particularly nitrogen oxides, alter atmospheric composition, air quality, and even affect global biogeochemical cycles vital for life. Furthermore, lightning contributes to the Earth's electric environment, climatic interactions, and even technological advances through scientific study. The next time a storm gathers and lightning streaks across the night, it is worth remembering that this brilliant flash is an active participant in shaping the atmosphere around us. It carries electric charge, spreads chemical compounds, fertilizes ecosystems, and signals the intense dynamism within weather systems. Nature's grand display is not just light, it is the visual signature of complex, interconnected processes that sustain the balance of our planet's atmosphere. And as your thoughts calm, wandering through these reflections, notice how something as fleeting as a lightning bolt continues quietly and persistently to influence the air you breathe, the weather you watch, and the world around us, all wrapped in a flash of brilliance before the thunder fades away. As our exploration of lightning's dance within thunderclouds drifts to a close, we are left in quiet awe of nature's raw electric ballet. Like a comet tail fading into the hush of space, let these sparks of knowledge gently illuminate your thoughts. Return to us, dear dreamers, as we journey further into the cosmic mysteries of Dreamtime science. If sleep has already taken you, may your dreams stay gentle. If you're still awake, feel free to let your mind wander back over the quiet marvels we've uncovered. When morning comes, you can always return for another Dreamtime tale, and I'd love to know which mysteries you'd like to explore next. Sleep now among the gentle stars. Until then, thank you for sharing this calm corner of the cosmos with me. Rest well, breathe deep, and I'll meet you again beneath the stars. Good night.